10 as a unit. Children count to 10 as a single unit. There are 3 ways children's lack of understanding of 10 is shown. Number 1, children do not organize into tens. They count the ones in the 10 to determine or confirm the quantity. They represent 10 with one object. Children who understand this critical phase can think of and count a 10 as a single unit thing. Combines 1 10 and any other number of ones up to 9 without counting. Children who understand this critical learning phase note that numbers from 11 to 19 are composed of 10 and a number of ones. So for example, when they have a 10 and 6 ones, they know they have 16. Decomposes numbers from 10 to 19 into 1, 10, and some ones. Children who understand this critical phase underline structure of these numbers. They know that the number itself tells them how many ones will be left over if they break the number apart into 1, 10, and some ones. Students can also count groups of 10. This means that children easily distinguish between the questions how many groups and how many together. They also know total instantly when the number of tens and ones is shown, and they know the number of tens that can be made from any group of ones and the number of ones left over. Children also know the number of tens in any 2-digit number. They know 10 more for any 2-digit number and know 10 less for any 2-digit number. Using symbols. Children who understand this critical learning phase know that numerals describe the underlying structure of numbers as tens and ones, and they can show 43 means 4 groups of 10 and 3 ones. Learning to add and subtract 2-digit numbers, the critical learning phases. Number 1, adding numbers to 20. Number 2, subtracting numbers to 20. In the critical learning phase number 1, adding numbers to 20, they can add 10 to any number of ones to 9 without counting. They subtract 10 from any number from 11 to 20 without counting. They add 2 single-digit numbers with sums larger than 10 by reorganizing them into 1, 10, and leftovers. And when adding 2 single-digit numbers that result in a 10 and some ones, they know what part of the number is needed to make a 10 and what part will be left over. After making a 10, they add the 10 and leftover ones without counting. So the critical learning phase number 2, subtracting numbers to 20. When subtracting single-digit numbers, knows what part of the number needs to be taken away to get to 10 and what is still left to take away. Subtracts from numbers to 19 by breaking up the 10 when necessary and knows how many left without counting. Critical learning phase number 3, adding numbers to 100. Children add multiples of 10 to 2-digit numbers without counting. They add 2 numbers up to 100 by reorganizing them into tens and leftover ones. Subtracting numbers to 100. Subtracts multiples of 10 from 2-digit numbers without counting. Subtracts from quantities to 100 by breaking apart tens when necessary and reorganizing what is left into the remaining tens and leftovers. Going back to the split strategy. Right here you will see an example of the split strategy where the number 220 and the number 310 were taken apart. They ended up with 530 after taking or splitting the number. In this other example, you will see the split strategy in subtraction, where they took the number 84 and the number 22 and split it to get the answer of 62. I will be attaching links to to watch the split strategy video that looks like this. Learning the structure of 3-digit numbers, the critical learning phases. Understanding the structure of hundreds, tens, and ones. Children counts 100 as a single unit. Knows total instantly when the number of hundreds, tens, and ones is shown. Mentally adds and subtracts 10 and 100 to and from any 3-digit number. Knows the number of hundreds that can be made from any group of tens and the number of tens left over. Determines total value of groups of hundreds, tens, and ones by reorganizing them into all possible hundreds, then all possible tens with leftover ones. Describes any given 3-digit number in terms of its value in ones, in tens, and in hundreds. Using symbols. Children interpret 3-digit written numbers with models of hundreds, tens, and ones, and records the number of hundreds, tens, and ones using appropriate symbolization. Going back to the jump strategy, this is an example of what the jump strategy is when we use a number line to add, subtract. In this first picture, you're looking at the number line that was used to subtract 89 from 49. 82 minus 49. And then they ended up with the answer 33. So you can see that they didn't count it by one. They actually counted 1, then 30, then 2 more. You can see how the number line is used to add. They started from the number 4 and jumped 10, then 2 more to end up in the number 16. I've also attached the link so you can watch this video on the jump strategy. And the shortcut strategy. You can see how to solve 51 minus 37, they added 37 plus 10, which equals 47. Then they added 4 more to equal 51. Then they added the 10 and the 4 to equal 14. So we know that 51 minus 37 equals 14. I will also attach the link to this video on shortcut strategy. Student invented strategies for addition and subtraction. Adding and subtracting 2 single-digit numbers. Adding 2-digit numbers. Subtracting by counting up. Takeaway subtraction. Extensions and challenges include bridging and larger numbers. I will be also attaching a link so you can watch this video on the bridging strategy. Standard algorithms. The standard or the traditional way of adding or subtracting. Most textbooks teach algorithm, but teaching only the standard algorithm does not allow students to explore other useful approaches. Students are usually introduced to the standard or the traditional way of adding or subtracting by their relatives, and they may resist the use of more flexible strategies. If you use it, you must understand why it works and be able to explain it. Rule must be used with standard and inventive strategies. We must remember that the responsibility for the explanation must be theirs and not yours. And once the standard algorithm is understood, it can be added as one more tool for your students to use. Do not introduce the standard algorithm methods to students before introducing other strategies. It is very important that you delay the use of standard algorithms. We want to delay this because once the standard algorithms are introduced, children assume that is the right way to do it, and it becomes difficult to suggest other methods. Thinking that mathematics is universal is wrong because there are a lot of differences between notation, conventions, and algorithms. Our job as teachers consists of actually researching our students' way of doing math in order for us to assist them. Learning more about what your students, particularly those from other cultural backgrounds, are doing, how they're doing the thing as they explore operations with numbers is often an opportunity for us to expand our knowledge. The standard algorithms for addition and subtraction. Standard algorithm for addition. Begin with models only and then develop the written record. In the beginning, we must just focus on regrouping without recording the numerical process and provide them with a place value met so they can actually see where the ones, the tens, or the hundreds go. We must place value charts to help our students record numerals in columns as they model each step for the procedure they do with the base 10 models. And this would be on step number 2, developing the written record. The standard algorithm for subtraction is similar to the addition one. We must first begin with models. We must also, for subtraction, we must anticipate difficulties with zeros, and then we can develop the written record. And what I mean about anticipating difficulties with zeros is that we must pay extra attention to the problems that include zeros because they give students special difficulties. So we must introduce some problems with zeros when we're still using models, so it is clear to them how to solve them. An estimate refers to a number that is suitable approximation of an exact number given the particular context. This concept of an estimate applies to measures and quantities as well as computation. There are 3 types of estimation. Measurement estimation, which determines an approximate measure without making an exact measurement. For example, we can estimate the length of a room or the weight of a watermelon. Quality estimation, approximating the number of items in a collection. For example, we might estimate the number of students in the auditorium or the number of jelly beans in the destination jar. Computational estimation, determining a number that is an approximation of a computation that we cannot or do not wish to determine exactly. For example, we might want to know the approximate amount we are spending at a store and need to add the cost of several items to see whether $20 will cover the amount. Many students confuse the idea of estimation with guessing. Computational estimation may be underemphasized in textbooks that focus on the standard algorithm, but it does appear in the Common Core state standards, and it is an important part of being able to do mathematics. Suggestions for teaching computational estimation. Using real examples of estimation. This means using real-life situations. Using the language of estimations, words and phrases such as about, close, just about, a little more than, a little less than, and between are part of the language of estimation. Using context to help with estimates. Situations play a role in estimation. For example, it is important to know whether the cost of a car would likely be $950 or $9,500. Accept a range of estimates and offer a range as an option. Since estimates are based on computation, how can there be different answers? Well, there can be different estimates because students use different strategies to get these estimates. It is important for us as teachers to not